This section introduces the core concept. We're going to explore how adjusting the settings, hyperparameters, in a specific type of machine learning model, called ElasticNet, affects its performance. ElasticNet is a regression model, meaning it predicts continuous values. Think of predicting house prices based on size and location. This is the core question. We are going to evaluate 4 different statements. I'm looking at how changing L1 ratio affects the balance between 2 types of regularization. Lasso, L1, and ridge, L2. Increasing L1 ratio means giving more weight to lasso. Here, I focus on the parameter alpha. A larger alpha leads to stronger regularization, resulting in a simpler model and pushing some coefficients to 0. Think of a simpler model as a less complex equation for prediction. Setting L1 ratio to 1 means we are only using lasso regularization, making it equivalent to a lasso model. Lasso is great at feature selection, discarding less important factors. If L1 ratio is 0, only ridge regularization is used. This means we use a ridge model. This type of regularization helps with multicollinearity. Conclusion: all statements A, B, C and D are indeed true statements about how hyperparameters work in an ElasticNet model. Awesome! I see L1 ratio as the dial that controls the blend of 2 different types of regularization. L1, lasso, and L2, ridge. Think of it like mixing paint. L1 ratio equals 0 is pure L2. All ridge. L1 ratio equals 1 is pure L1. All lasso. And values between 0 and 1 give you different mixtures. It directly impacts how much each regularization technique influences the model's final parameters. Neat, huh? The ElasticNet model is actually a clever combination of lasso and ridge regression. It uses both L1 and L2 regularization simultaneously. This gives you the benefits of both approaches. LASSO's ability to perform feature selection by shrinking some coefficients to exactly 0, and ridge's tendency to produce more stable models, especially when you have many correlated predictors. I view alpha as the overall volume knob for regularization. A higher alpha means stronger regularization. It pulls the model's coefficients closer to 0. The result? A simpler model, which ideally avoids overfitting and enhances generalization to unseen data. A lower alpha means weaker regularization, potentially leading to a more complex model which could overfit if the regularization is too weak. It's crucial to find that sweet spot. I see that you're asking about the effect of increasing alpha in ElasticNet regression. Think of alpha as a dial controlling the strength of regularization. A higher alpha means stronger regularization, forcing the model to use smaller coefficients. Smaller coefficients mean a simpler model, less prone to overfitting. It's like pruning a tree. You're removing unnecessary branches, coefficients, to make it more manageable and less likely to be blown over by the wind, overfitting. Let's focus on L1 ratio. It's a percentage, or a weight, that determines the blend of L1, lasso, and L2, ridge, regularization. When L1 ratio is 0, it's pure ridge. Think of it as a recipe. 0 L1 ratio means 100% ridge recipe, only using ridge regularization. Similarly, when L1 ratio is 1, it is pure lasso. It's a 100% lasso recipe. You're using only lasso regularization. If L1 ratio is between 0 and 1, you're using a blend, a mixture of the two, blending ridge's smoothness and LASSO's ability to shrink coefficients to 0. Increasing L1 ratio means increasing the weight of lasso penalty relative to ridge. More lasso, less ridge. This makes the model more likely to choose some very specific features, because it pushes more and more coefficients towards 0. I'm talking about a powerful regression model that combines the best of 2 worlds: lasso, L1, and ridge, L2, regularization. Think of it as a smart blend. It borrows the strengths of both to improve predictions and avoid overfitting. This is a crucial control knob. In ElasticNet, it decides the mix of L1 and L2 regularization. A value of 0 means pure ridge regression, 1 means pure lasso regression, and anything between 0 and 1 is a combination of both. This hyperparameter sets the overall strength of the regularization. A larger alpha means stronger regularization. This reduces model complexity by pushing some coefficients toward 0. Think of it as a volume control for the regularization. These are two types of regularization techniques that help prevent overfitting. Lasso, least absolute shrinkage and selection operator, adds a penalty proportional to the absolute value of the coefficients. It tends to shrink some coefficients to exactly 0, performing feature selection. Ridge, L2. Regularization adds a penalty proportional to the square of the coefficients. It shrinks coefficients towards 0 but rarely sets them to exactly 0. This question tests your understanding of how changing the alpha and L1 ratio hyperparameters in ElasticNet regression affects the model. ElasticNet combines two types of regularization: lasso, L1, and ridge, L2. We'll explore how these hyperparameters control the balance and overall strength of this regularization. These are the possible answers to the quiz on ElasticNet hyperparameters. I will check each statement for accuracy. L1 ratio controls the mix of L1, lasso, and L2, ridge, regularization. Increasing it means you're giving more weight to the L1 penalty. Lasso is known for shrinking some coefficients to exactly 0. Think of it like this. Increasing L1 ratio is like turning up the dial on LASSO's feature selection ability. If L1 ratio is 0, only the L2 penalty, ridge regression, is active. It's like saying, I want only ridge regularization, no lasso at all. When L1 ratio equals 1, only the L1 penalty, lasso, is active. It's pure lasso, no ridge involved. Alpha determines the overall regularization strength. A higher alpha means stronger regularization, resulting in smaller coefficients, and some may even become 0. This leads to a simpler model by reducing complexity. It's like saying, I want a less complex model, so let's shrink the impact of every feature. We're diving into the amazing world of ElasticNet, a powerful tool in machine learning for regression tasks. We'll explore how to tune its hyperparameters, alpha and L1 ratio, to build the best possible model. Get ready to become an ElasticNet master. Think of L1 ratio as a volume control. Increasing it turns up the volume on the lasso penalty, making its effect stronger. Remember, lasso is all about shrinking some coefficients down to exactly 0, which means you're selecting the most important features. When you set L1 ratio to 0, you're essentially telling ElasticNet, use only the ridge penalty. It's like turning off the lasso part completely. You're left with a pure ridge regression model. Setting L1 ratio to 1 does the opposite. It selects only the lasso penalty. This gives you a pure lasso regression model, focusing on feature selection through coefficient shrinkage. Imagine alpha as a regulator. A higher alpha means stronger regularization. This forces the model's coefficients to be smaller, often resulting in several becoming 0. Fewer non-zero coefficients directly translates to a simpler, more interpretable model, reducing the risk of overfitting.